Okay, let's get started. So today's lecture used to be in previous years taught in a series of 3 lectures, but it's condensed into 1 lecture to make room for us to build LLMs from scratch, which is going to take about 3 to 4 weeks. So it might feel we are rushing quite a bit, but I think the slide, like the lecture slides, are very self-explanatory. So take your time and you can study yourself or re-listen to the YouTube video, which is going to be uploaded sometime this week. Okay, so last time we introduced some of the keywords in optimization and laid out what we're going to cover. And I keep updating the lectures every year. This year, we're going to strengthen the diffusion and we're going to add in flow matching and KB cache compression, which is a hot area these days. Okay, so today I'm going to introduce you what it means to classify the task of classification. And to do that, we need to define score functions, define loss functions, define computation graph, and backpropagation. And now we're ready to train a neural network. Okay, so what's a classification problem? So typically you're given a set of discrete labels. So in this image classification task, this is predefined set of labels, dog, cat, truck, plane, etc. And upon given some image input here, you're supposed to output the correct label cat. And we're going to try to find some function parameterized by data that does this given the training data and hopefully generalizes to previously unseen data set. Okay, so it's completely meaningless if you memorize the training set because you won't be able to generalize to previously unseen image. For example, here, let's say there's I don't know, a potted plant here. This is supposed to be a plant. Now it's a different image. It's not in your database, so you cannot classify. We don't want this to happen. We want to train some F such that it generalizes to previously unseen data. Because otherwise, what's the point? You can just put all of this training data. So last time we said training data is a tuple of data and label. Otherwise, we can just put this in a hash function and upon receiving an exact match, output some label associated with it, right? So there's nothing to learn if the goal is to memorize data set. It's like, someone memorizing a previous year's exam, and when I change the exam, you completely fail the exam. We don't want this to happen, right? You want to understand the underlying mapping between image space to some label space, right? Okay, so, just additional announcement. I'll make the previous year's exams available online on ETL. So I heard anonymously that someone is selling previous year's exam with money, and I don't want that to happen. So it's going to be made available, okay, for free. So that means you need to generalize. You cannot just memorize previous exam and hope magic happens. Okay, so the computer sees, for us, we already see, our brain already pre-processes the image into some abstract form. but the computer doesn't have any of that. It just sees an array of these numbers, and it's supposed to figure out the correct mapping from image space to label space. So it's a hard problem. Also, in real life, you're almost never going to encounter exactly same image twice. So things keep moving, and you have background clutter, and you have occlusion. So this object here is occluded, and you have pose changes. So you have different deformation, and you need to train a classifier that's robust against all these input variations. And typically, to train these models, there are famous benchmarks. And this is toy dataset, and it's called MNIST. Why am I bringing this up? Because it's an important keyword. So when people talk about MNIST, sci-fi, you need to know these words. It's a dataset created for digit classification. So these are created 28 by 28 small images. It has been already split into training and test images. And these are from human handwritings. And SciFar, there's also SciFar 10 and SciFar 100. SciFar 10 for 10 classes, SciFar 100 for 100 classes. It's also a small image, 32 by 32, but this is color image, and 50K training, 10K testing. And there's also ImageNet with 1,000 classes and 1.2 million training images, 100K test images. And SciFar, I would say it's a solved problem. If you look at the classification accuracy, you get perfect score. And so is ImageNet. So I would say these are for sanity checking your custom build classifier and see if it's doing something correct or not. Okay, so now really try to understand what's under the hood to make this happen. Okay, first I'm going to introduce score functions. Okay, so a score function is a parameterized function. It takes data and outputs a real vector, which is of dimension c by 1, where c is number of classes or cardinality of your label space. So that maps input x to these real vectors, and these vectors are called score vectors, S. And like I said, it's of dimension c. And each element here corresponds to score that the classifier assigns to a specific class index j. Okay, and it has parameter theta, and theta is what we are gonna optimize. That's the optimization variable. And once you have this f, okay, let's forget about training f. Let's say somebody gave you an f. How do you predict the label? How do you, in other words, run inference? So in machine learning, the notation is if you put a hat, that means a predicted label. Okay, so you're going to take this vector, and if you take the argmax, then that's going to be your predicted label. In other words, you want the score for the ground truth class to be higher than the score assigned to other classes. That's the goal, or that's an ideal score function. Okay, because we're going to predict based on this logic here. Okay, so we want the score for yi to be greater than score for all other classes j, such that j is not yi. And note that these are not necessarily probabilities. They are unnormalized preferences for each class. And we're going to learn, the next section will be on the loss function. And loss function will enforce the correct class receives a higher score than others. Otherwise, the loss function will enforce this will happen. And the optimization, we discussed optimization last week. And the objective here is going to be the loss function measured using scores, and the optimization variable is the data. And optimization algorithm is going to be gradient descent. Okay. Okay, so here's a very simple parameterization of an example's classification model. So you're given an array of 32 by 32 by 3 images, 3 image. So this is height, width, and channel. And given x, so this is x. What we're going to do is we're going to flatten this into a 1D vector. Okay. And then we're going to multiply by a matrix of size C by 3072. And then we're going to add in some bias of size C by 1. And the output is going to be C by 1. So we're going to interpret this as a score where each entry corresponds to the model's score for the image X to belong to that specific class index J. Okay, so we have 2 parameters actually in this case. So notation wise, this semicolon means before, that's the input. After semicolon, that's the parameters. And we're going to optimize over these variables. Okay, so for example, if I'm given this 2 by 2 image, I'm going to flatten this into a 1D vector here. And then I'm going to multiply by this matrix and add in some bias. And I'm going to interpret the output as the class scores. So I'm going to give some arbitrary ordering. So I'm going to interpret the first one as a cat score, second one as a dog score, third one as a sheep score. And this is not a good model because the score for the cat score, for the cat class, is not greater than the score for other classes. So this is a really bad model actually for this typical, for this example image. So we're going to have, like we saw in the previous data set slide, we're going to have millions of training data. And on average, we want the loss function to be as low as possible. So I'm going to skip a bunch of slides because there are so many things to cover today. How many slides? Okay, so we have 72 slides, and I'm not going to cover every slide. Okay, so for example, let's say we're given this image. Okay, let's just look at this one example. And we have 10 classes. And what's the score for the ground truth label? That's this guy. So this is not higher than score for all other classes. So this parameter W is not very good for this input image, because we want this to be as high as possible, higher than all other class scores. And this example, score for automobile is higher than all others, so this is good, and etc. Okay, so we showed you a very simple parameterization, and haven't really thought about. Okay, so the important question here is, okay, so let's say somebody gives you a score function and the model. How do you quantitatively measure how good this model is? Because without this, we cannot write down the optimization problem. That's where the loss functions come in. So loss function takes the input and outputs. So sorry. Let me take a step back. So we already discussed score functions. So let's say we're given a score function f, and takes input and outputs c by 1 vector of scores for all classes, parameterized by data. And the loss function is a map where it takes the output of the score function, which is of size c by 1, and the correct ground truth label, this is supposed to be ground truth label, and outputs a real number, a scalar. And we're supposed to interpret the output as a measure of how good the score function is. So it takes output of the score function and ground truth label corresponding to the input to the score function, and outputs a real number. And it measures how compatible the prediction is with the target label. Target label, ground truth label, they mean all the same thing. People use it interchangeably. In medicine, they call it gold standard, but they all mean the same thing. Okay, given data set, we're going to come back to this word later, empirical risk. It just means loss measured on this specific data set. So loss typically is average of the individual losses, where individual loss is loss measured on individual examples. Okay, so input xi comes in, gets passed through the model. Model outputs c by 1 score vector, and given the output of the score function, and given the correct ground truth label, the loss function measures how good this prediction is and outputs a real number. An average of that, where average is taken over the data index, that's the loss function of the model parameterized by data. Okay? So with bias, this is going to be tuple of the weight and bias for this linear model. Without bias, that's just going to be the weight. And to write this more specifically, we're going to use semicolon and corresponding parameter. So the pipeline is input data comes in, gets passed through the score function, outputs a c by 1 vector, and gets passed to the loss function with the corresponding label, and outputs a real number. Okay, and this is parameterized by data. That's going to be the parameter, and we're going to do a gradient descent to minimize the loss. That's the whole pipeline. Okay, so the next step is you compute this over all data points I, you average that, and we're going to take the gradient descent on the parameter. Okay? And that's it. That's everything. All right, so what are some example loss functions that's a popular choice? We're going to discuss two choice of loss functions for classification. One is called multi-class hinge loss. So given an example xi, yi, the hinge loss has the form like this. It sums over all class IDs that is not the ground truth ID. And it takes max of 0 and your function argument. So this figure shows y-axis is the output of the hinge for this example I, and x-axis is score assigned to the ground truth label. So if the score for any other class J that is not yi, if it's greater than 1 plus any Sj, then you have a loss of 0. Otherwise, you're going to incur loss proportional to how far you're off. And I can also write this down in terms of inequality. So loss of 0, hinge loss of 0, implies what inequality among the square vectors? Yes? Right. Okay, we want the score for the ground truth to be at least 1 larger than any other class. Okay, why 1? Just convention. It's supposed to provide some robustness. So suppose your input, so this S is passed through a score function, and it comes from image xi. So say we perturb xi by epsilon. Okay, add some salt and pepper noise, or add some background clutter, or any noise. Then we don't want the score so close to Sj, so that if there's a very slight change in the lighting or occlusion or whatever, we don't. So let's say this is like 0.87, and this is 0.869. Let's say the image looked something like this. There was a person standing with arms up. Xi plus some noise. Okay, so let's add some salt and pepper noise. Now the score changes. We don't want this to happen. So in order to provide some robustness against input variations, we're going to enforce that the score for the ground truth label to be at least 1 greater than the score for other classes. So this is called the margin. And it really, in practice, it trains a more robust classifier against input variations. Another loss that is more popular is multinomial logistic loss. So what you do is you want the probability, so given some input xi, you want the probability assigned to the ground truth class to be as high as possible. So how do you do that? You first turn this into log probability. So forget the log term. How do you get this unnormalized score vector to a probability? And like you saw here, it also has some negative numbers, right? So easiest way to do this is, first exponentiate, and then normalize, meaning you sum everything and divide it. This is the quickest way to turn a real vector into probability vector. And you want to maximize log likelihood or minimize negative log likelihood, meaning you want the class probability for the ground truth to be as high as possible. Here, you don't need to worry about with respect to other classes because they all come into denominator. Okay, so if you increase the probability, it's going to automatically enforce this. Okay. All right, so we already discussed this part. And one another thing that's important is, suppose you found W such that loss is 0. So now the question is this W unique? So in this example, we're using a very simple linear model. And the answer in general is no. So if all examples satisfy the margin constraint, meaning the score for the ground truth class is at least 1 greater than score for all other classes, then if you scale W by a constant, you're still going to have 0 loss. So for example, if you multiply by 2, it's still going to be 0. So this choice of W is not unique. And this is very hand wavy, I know. So if you take my machine learning class, we do more theoretical analysis. But here for our undergrad class, we're going to introduce regularization more conceptually. So given some training data, there may be many, so this is a regression task, not a classification task. There may be many different models that perfectly capture the training data. So let's say we're given 2 types of model, F1 and F2. And so these green data points are our training data. And these pink dots are test data. So if we use very complicated model, then we're going to have very high deviation here. But if you use a simple model, then your deviation is going to be smaller conceptually. So the regularization function quantifies the complexity of the model, and it penalizes complex models. So do you always prefer simple model versus complex model? Not necessarily. So if you use too simple model, then you're going to underfit, meaning you're going to not capture the variations in the training data. So you want to at least have small loss on the training data. Otherwise, there's no hope for generalization. So you need to have some reasonable performance on the training data before you talk about generalization. So simple models underfit and complicated models overfit. So we talked about data loss. So we talked about multi-class hinge loss, logistic loss, and we're going to add in some hyperparameter times regularization so that we can generalize better for previously unseen data. And there are many different ways to regularize a model, and they're all connected to statistical learning theory. And and we're going to come back to this later. There are many different variations. And if you use L2 norm of the weights, that's connected to maximum a posteriori inference from statistical learning theory. And if you use L1 norm, that's connected to leading to sparse solutions, meaning your parameter is going to have lots of zeros. And we're going to come back to this in network pruning lectures. Another famous norm is nucleus norm or trace norm. It's nothing but the sum of the singular values of the matrix. And you can interpret this as L1 norm on singular value vectors, which leads to sparsity among the singular values. So this is going to lead to low rank solutions. Yes?
Don't we have to talk about the convergence of gradient descent algorithm?
Yes, yes. So unfortunately, this is going to be out of the scope for this class. But we do cover it in the machine learning lectures, which is a graduate level class. Yeah, so to talk about the convergence of the gradient descent, we need to make some assumptions. So we need to assume this objective function is convex, and our feasible set is also a convex set. So under that assumption, we can prove the convergence rate of the gradient descent algorithm. And if we know more and more about the function, like strong convexity and beta smoothness, then we can prove more strong convergence results. Okay, so far we talked about classification problem, score functions, loss function, and now we're going to talk about computation graph. And this addresses how we're going to compute the gradient more efficiently. So far, we only discussed linear model. But we're going to soon encounter very, very complicated models, like LLMs and many different stuff. So there, you cannot analytically derive the gradient yourself. It's too complicated. So we're going to introduce computation graph and systematically compute the gradient very efficiently. So what's the definition? A computation graph is a DAG, a directed acyclic graph with vertices and edges. And the node represents either an input, a parameter, or some computation operation. So distinction is a node could be some, I don't know, matrix multiply. So this has a parameter. Or a node doesn't necessarily need to have a parameter. So for example, it could be doing something like this, f of x, element-wise, takes max of 0, x. Otherwise, kills all negative values to 0. This doesn't have any parameter. Nothing to learn here. So for input nodes, the value is applied externally from data set. Or loading some other model parameters. For non-input nodes, each node is associated with a function which may or may not have parameter and computes its value from output of its predecessor nodes. It's a DAG, so it has topological ordering, so it has a predecessor and children nodes. Edges indicate the output of node U is used as input to node V. Okay, it's directed, so there's clear ordering and of input and output. And computation is for any node that is not an input node. It's associated with the function fv, and what it does is it collects the output from its predecessor and use it as input to evaluate its given function f of v. Okay, so it collects the output of all the predecessor nodes into a set or list and runs it through its own function and passes the output to its children nodes. And we already talked about input and outputs. So there are designated input nodes and output nodes. We already said input nodes load data set or load parameters from some other model. And output typically in classification is a single number indicating the loss itself. Or for regression, it's going to be something like MSE, mean square error. But it doesn't have to be a scalar output. It can be any number of outputs. So overall computation computed by the graph is a function that takes maps its inputs to outputs via composition of the functions. So we're going to talk about any DAG. So now our function is going to be much more powerful. So far we stuck to easy linear models, but now it's going to be any DAG. Okay. So in deep learning, this computation graph abstraction allows us to represent forward paths and backward paths. So backward paths, backpropagation, they all mean the same thing. So forward pass is loading the data, computing the loss. And backward pass is, like the name suggests, start from the loss and compute the gradient of the loss with respect to the node itself. And you start from the loss and backpropagate or compute the loss to the left all the way to the input node. And if you do one forward pass, one backward pass, that's going to compute the gradient of the loss with respect to the input. Okay, so this is an example computation graph where it's doing a linear model computing the hinge. So you're given the input data and parameter W, and they get multiplied to compute the class scores, and you have this hinge node, and you have the regularizer, and you add them up, and that's going to be your final objective. And there's no single best computation graph. you can just enumerate all these atomic operations into multiple set of nodes, or you can just shortcut and predefine this hinge loss compute node. Okay, so let's do a very simple example. So we have this computation where there are three inputs, x, y, z, and all it does is it adds x and y and multiplies it by z. And here inputs are -2, 5, and 4. And we're going to do a forward pass and backward pass. So forward pass and backward pass, okay. And before that, let's pre-compute some useful intermediate steps. So adding x and y, we're going to call the output as q. This is this is going to be q times z. And derivative of derivative of q with respect to x and y is 1. And f now is q times z. Derivative of f with respect to q is z, and derivative of f with respect to z is q. And we want to compute the gradient of the output with respect to all the inputs. That's all we want. So to do that, we're going to start from the right. So for forward pass, we go left to right. For backward pass, we go from right to left. So forward pass, we already have, okay, so forward pass is q is x plus y, that's going to be 3. And f is q times z, so q is 3, z is -4, that's -12, so that's forward pass. And backward pass, always, so why are we discussing this? So that we want to have a systemized code that can do this automatically for us. So I often think about this as 1D dynamic programming, where you reuse computation from previous step, and the base case in the backward pass is, in almost all cases, going to be initialized to 1. So it's the derivative of output with respect to itself. Okay, given 1, df dz is q, so q is recomputed with 3. df dq is z, z is -4. So we have already computed this guy, df dq here, and we computed df dz, this guy. And now we want to compute these guys. So df dy is, we're going to use the intermediate computation we have already done. That's by chain rule, df dq times dq dy. df dq we have already computed, that's -4. dq dy is 1, so it's -4. df dx, same thing, chain rule, df dq times dq dx, -4. So here, what we've done here in this step is we have used pre-computed df dq and used chain rule. So from the perspective of this computation node, this guy is called upstream gradient, and these two guys are called downstream gradient. Okay, so from the perspective of a single computation graph, a single computation node, you have some function f. In the forward pass, you compute given x, y, the output of the predecessor. That's going to be z. That's the forward pass. During backward pass, the definition of the function, the computation function or computation node, is going to have already baked in internal method that computes the local gradient of the output with respect to the inputs. That's part of the implementation of this f. So during backprop, you're given as input the upstream gradient, which is the gradient of the loss with respect to its immediate output. Given the upstream gradient, you're going to do a chain rule. You're going to multiply the upstream gradient by its local gradient of the output with respect to x. That's going to be dl dx, and that's going to input to its predecessor as the upstream gradient. So upstream gradient always is basically gradient of the final output, which typically is a loss, with respect to the outputs. So that's how we're going to code this systematically, so that we don't have to do any analytic gradient computation. Okay, so each computation node has two methods. One is how to compute the for given inputs, and the other is, and in the for process, you need to store in the member variable whatever is necessary to compute and pass gradients to its predecessor. And during backprop, you're going to take as input upstream gradient, and you're going to multiply by local gradient, which is predefined, and pass the upstream gradient to the predecessor. And if you chain any of these computation nodes, you're going to, once you run forward and backward for each training data, you're going to automatically compute the gradients for all parameters. And you're going to collect all these gradients with respect to all parameters and apply gradient descent. And that's how we're going to train neural network. Okay? Okay, so another example. Let's skip this, and if we have time, come back to this. So this is just a slightly more complicated example. And let me see how many slides I've left. Okay. Okay, let's be safe and let's skip this. All right, so we said our computation graph can be any DAG. So it's very possible that a single computation graph has multiple outputs. Okay, so for example, let this F have two outputs. It's passing its output to this guy and this guy. Then in this case, how do you compute the upstream gradient to the predecessor? So that's simple chain rule. So df dx, that's simply adding up this upstream gradient, this upstream gradient. Okay, so it's going to add, it's going to collect all the outputs, all the Qs, and multiply dq dx, and add them up, and that's going to be your df dx. Okay. So typically, our computation nodes are not going to really deal with scalars. So it's going to deal with vectors and matrices. So in this case, the local gradients are going to be gradient of the output vector with respect to input vector, which is going to be Jacobian matrix. So the meaning is derivative of each element of Z with respect to each element of X. Okay. So here's a vectorized example. So if you, I think the prerequisite calculus class walks you through multivariable calculus. So I don't need to discuss all the details. So let's say we have this L2 norm. So you take W and X, multiply them here, and take the L2 norm. So let's give this guy a name. That's Q. So Q is W times X, which is this matrix, 2 by 2 matrix, times a vector of 2 dimension. And L2 norm of that's simply L2 norm squared. That's simply each element squared and summed up. So that's the 4 pass. You take Wx, do a multiply, matrix vector multiply, take the L2 norm, that's going to be your output. So that's the 4 pass, which is the easy part. And now we need to compute the backprop. So if you're already familiar with multivariable calculus, you can jump from here to here automatically, right? So that's L2 norm, and that's Q transpose Q. And this guy, if you take the gradient with respect to the vector Q, that's 2 times Q, right? Or you can derive it yourself, right? So this is going to be the definition of L2 norm. And if you want to take the gradient of this guy with respect to one of the component, say Qi, then everything vanishes except Qi squared, right? So it's going to be d Qi of zeros plus Qi squared plus all the zeros. That's going to be 2 times Qi, right? Do this, repeat this process for all elements, form a vector, that's going to be 2 times Q, right? Or you can just go straight here. All right, so so always the gradient of the output with respect to itself is going to be initialized to 1, right? And how do I compute the output? Sorry, the gradient of the output f with respect to q. So remember, this is q. So the answer was 2 times q. So how do you compute the upstream gradient? It's whatever the upstream gradient, which is 1, times 2 times q. So just take this guy, multiply by 2. That's going to be your gradient here, right? All right, so how about, so now we have backpropagated one step. So this is gradient of the final output with respect to q. And now we need to distribute it and compute the gradient here and here. And then we're done, right? So in order to do that, given this as the upstream gradient, we need to compute or define the local gradients. How do you compute the gradient of the output with respect to w, gradient of the output with respect to x, which is write it as gradient symbol. Gradient with respect to w of the q, and here you need to have the local gradient defined, gradient of q with respect to x, right? And then multiply this upstream gradient. Now we're done, right? All right. So gradient of the q, this guy, that's q, with respect to individual components of W. How do you compute that? So here, take this guy and think about how you're going to compute the gradient of this guy with respect to Wij. So let's take kth element of Q and differentiate it with ijth component of W. Okay, so I'm going to take the kth slice here. Okay. And then differentiate it with respect to Wij. Obviously, we're going to have 0 unless k is equal to I. If k is equal to I, so just to write it again here cleanly, if k is equal to I, then the parameter corresponding to this guy, that's going to be the output. So it's indicator of k equals to I times xj. Okay, so here everything vanishes except wkj xj, and this is going to be 0 unless k is equal to I, right? And the output is going to be x equals j if k is equal to I, right? And you write that using the indicator function. This is 1 or 0. 1 if the expression is true, 0 otherwise. So we're going to see this a lot. This is called indicator function. If I write it like this, this is going to be 1 or 0. 1 if k is equal to I, otherwise. And another expression we're going to see a lot is something like this. So A is typically set in this case. So this is going to be 1 or 0 if element A, small a, belongs to set A, otherwise. All right, so we need to compute the gradient of the final output with respect to Wij. That's by chain rule, df dq times dq d Wij. df dq we have computed as 2q, and dq di, dq dWij we computed above. And sum this, that's going to be 2qi xj, or if you have learned multivariate calculus, you can just skip everything here and jump to the conclusion immediately, because that's Q transpose Q and X transpose W transpose WX, right? So we just need to define gradient of this guy with respect to W. Gradient of this guy with respect to X. And you're done immediately. Okay? This is 2QX transpose. And how about here? let's look at the solution. That's 2W transpose Q. Right? So you can do it element-wise, or you can just use the formula that you remember from your calculus class. So here, okay, let's continue. So here we have computed the gradient 2 times Q times X transpose. All right, so you take 2 times Q times, and that's going to be this red box here. And now we need to compute the df dx. And you can go through each elements, or you can use multivariate calculus. And that's going to be 2 times W transpose times Q, which is equal to this guy. Right? So there seems to be some patterns, right? So if you have an addition node, it just distributes the gradient with identity, right? It just multiplies 1 and passes the upstream gradient to its downstream. If you have the multiply gradient, it swaps its value. So here you're given upstream gradient of 5 for 2 times 3 equals 6. And its upstream gradient, you take the upstream and multiply by its other input, that's 15. Take the upstream gradient, multiply by its other input, 10. So it swaps the multiplier. And sometimes you will have parameterless copy gate, where it distributes out the 4 pass outputs to multiple locations. Then during backprop, you're supposed to add in its multiple outputs by this chain rule here that we discussed. And if you have the max gate, where it takes all its inputs and outputs max among its inputs, then it routes the gradient to its argmax. All right, so we don't ever want to do this analytically with hand. So how do we systematically write this into code? So that once we define the computation graph, it automatically runs forward pass and backward pass. So the way to do this is, for each node or computation node, you need to define 2 things: forward pass and backward pass. Forward pass is given 2 inputs, x and y, and return z, which is multiply, for this example, multiplying all its inputs. And here, it saves x and y, it caches them so that we can use them during backprop. Okay, so during backprop, we need to, we're given the upstream gradient, grad z here, that's the upstream gradient, and we're multiplying these cached values to compute the upstream gradient for its predecessor. Okay, and it outputs 2 things: dl dx, dl dy, right? So once we have defined the computation nodes, we can chain them, form a DAG, and we just need to define the input, and it's going to automatically load the data, pass it through the computation graph to compute the loss. And once we call backprop, it's gonna, compute the backpropagation and automatically compute DL, the data I, for all the parameter nodes. And we collect this into a long vector, first parameter, second parameter, etc. Concatenate it into a long vector, and then apply gradient descent. Okay. And the disclaimer is that almost all neural networks are going to be non-convex. So it's going to be extremely unlikely that you can theoretically guarantee convergence. And in practice, so we're going to cover more about optimization in the next lecture. We're going to make it converge to local optimum, but it's not even guaranteed because we keep decaying the step size, and eventually we're going to go to a point where gradient gets multiplied by a very, very small step size. So it's going to stop somewhere, but we're not even going to guarantee local optimum. Because two things. One is the function that we create, our DAG, is not convex. And we're going to use stochastic gradient descent. So, because the full gradient requires looping through all the data points. So for example, ImageNet had 1 million data points. To compute one gradient, we need to load and pass through 1 million data points. And that's going to take forever to compute one gradient. So what we're going to do in the next lecture is we're going to try to approximate the gradient so that we just randomly sample a mini batch of data and approximate the full gradient with sample gradients. And that's another hurdle to show any meaningful convergence results. So in PyTorch, this is a framework that we're going to use to build LLMs. They already have defined all these different modules so that it's very, very unlikely that you will need to create a computation node yourself. Create means define these forward pass, backward pass in a custom node. And since many of them are already defined, you will most likely think about compositioning different pre-built computation nodes into a new graph rather than creating a single node yourself, because most of the computation nodes you can think of is already made available. Okay, so I think we covered most of the materials except the sigmoid, and since we have a little bit of time left, let's try to cover this as well. So this is just another example for a slightly more complicated computation graph. So we're going to come back to this function later. So what it does is takes three inputs in this case, x0, x1, and it has three parameters, w0, w1, w2. So this is your parameter. Takes two inputs. And does linear combination and multiplies -1, exponentiates it, adds 1, and divided by and inverted. That's the output of a sigmoid function. So forward pass is pretty straightforward. You can just take inputs, compute whatever is inside the node. How about backprop? For For these intermediate nodes, the local gradients exponentiating, you get e of x. Df dx for multiply, you get a. For the inverse, you get negative 1x squared. Adding plus, you get 1. So let's do some backprop until the time runs out. And df dx here for this last step. Always the upstream gradient is initialized with 1. So you're supposed to multiply negative 1 divided by x squared. And you take upstream gradient of 1 and take this guy, square it, and inverse it, multiply negative 1. That's going to be negative 0.53. And you can carry on this backprop computation, and you're going to arrive at all these red points. You can also do a shortcut. So this is the most atomic version you can think of. But typically, you don't want to do this because it's tedious and slow. So you can realize. So this is called a sigmoid function, which takes the input, multiplies negative 1, exponentiate 1 plus, and 1 over. So you can take a shortcut here. So what is the gradient with sigmoid with respect to input? If you do this, it's basically 1 minus sigmoid times sigmoid. So we can take a shortcut here. So the output of the sigmoid was 0.73 multiplied by 1 minus that. That's 0.20. So this whole thing can be replaced with the sigmoid computation node to save some computation, as opposed to doing all these computations along the way. So as you can probably imagine, this is already implemented in PyTorch. So you don't need to do these atomic steps. All right, that's it for today's lecture. Thanks.